Hello, everybody. I hope that you have been enjoying the course so far. I know that there are some topics which you may find difficult to understand. So, for that, I would recommend you to please go through my lectures, both the PDF files and also the video lectures, as much as you can to understand. You can even Google for some of the concepts if you want. Uh, Today, we will be talking about another equally important concept in handling statistical data, and that concept is actually known as the logistic regression. This is very popular in classification of objects when you have qualitative response, for instance, and actually that's what we meet in reality a lot. So let's start. The linear regression, recall that the concept of linear regression assumes that the response variable y is quantitative, right? That's what we discussed last week. We discussed simple linear regression when we had only one predictor and one response, and we also discussed multiple linear regression when we had lots of predictors but only one response variable y. However, in many real-life situations, the response variable is instead qualitative. For instance, eye color. It can be blue, green, brown. For example, email. Emails can be classified as a spam email, non-spam email, junk email, for instance. Bank transactions, for instance, fraudulent or not fraudulent bank transactions. So all these three variables, they are actually qualitative in nature, right? So often such variables are referred to as the categorical variables because they have some kind of categories, or they are defined in terms of categories. Predicting a qualitative response for an observation can be referred to as classifying that observation. You intend to classify your data whether it belongs to eye color blue category or eye color green category or eye color brown category. Similarly, you have lots of emails with you and you wanted to classify them whether they belong to a spam folder, non-spam folder, or a junk folder. So you have classified them in three, you have classified the whole data into three groups: spam, non-spam, and junks. Similarly, bank transactions, they can be considered as fraudulent or not fraudulent. So you have two categories and you wanted to classify all the transactions into two groups, right? So classification behaves like a regression method in a sense that it predicts the possibility, or in statistical terms, probability of each of the categories of a qualitative variable. When we classify our transactions, for instance, in two groups, fraudulent and non-fraudulent, I can build a model based on my existing data and decide what is the probability that my new transaction will belong to a category fraudulent or a category non-fraudulent. Similarly, based on my existing data, I can build a model, and then that model can help me to assist or to somehow assess if I receive a new email, does it belong to a spam category, non-spam category, or a junk category, right? So that's why this method is very known, very popular in many ways in data analytics or data handling. So let's move on. Can a linear regression be used for classification? Again, remember, classification means when you have classes, when you have categories, right? When you have qualitative response variable. Can we use a linear regression method to do that? Suppose that we are trying to predict the medical condition of a patient in the emergency room on the basis of her symptoms, right? So in this simple example, there are three possible diagnoses: stroke, drug overdose, or epileptic seizure. The patient was recognized or diagnosed by any of these three categories, right? So we can consider what one option comes into our mind, that why not use encoding? Why not use some kind of numerical codes and specify those codes to those qualitative variables or qualitative categories, and run a simple linear regression, right? So say I said y equals to 1 if it is stroke, if the patient is diagnosed with stroke. This will be 2 if patient is diagnosed by a drug overdose, and this will be 3 if a patient is diagnosed by epileptic seizure. Now using this coding, we can fit linear regression model because now we have all the values in numbers. And then we can use that model to predict Y on the set of predictors, right? But does it give us a right prediction? What do you think about that? Think a moment. Think what this coding means to this particular problem, and what will happen if we run a linear regression to this particular example. What kind of results are we going to get? Now, notice what happened when we code qualitative response in this way. First, this coding rather implies an ordering, not the outcome. For example, putting drug overdose in between stroke and epileptic seizure, that's what we did actually. We say 1 for strokes, 2 for overdose, and 3 for epileptic seizure, right? So now drug overdose is in between strokes and epileptic seizure. Similarly, strokes comes before drug overdose, and epileptic seizure comes after the first 2 categories, right? Now, it insists that the difference between stroke and drug overdose is the same as the difference between drug overdose and epileptic seizure. Now go back and see. Stroke was defined as 1 and drug overdose was defined as 2, right? So 2 minus 1 is 1, right? Similarly, epileptic seizure was defined as 2 and drug overdose was defined as, epileptic seizure was defined as 3 and drug overdose was defined as 2. Again, the difference is 1. So what does it mean? Does it mean that the difference between stroke and drug overdose is exactly the same between the different with the difference between drug overdose and epileptic seizure? Does it mean like that in reality in medical practices? Of course not, right? Now try, what if we try another coding sequence, for instance? Now you say, okay, epileptic seizure, some of you come up with another coding style and say, okay, now I put 1 for epileptic seizure, 2 for strokes, and 3 for drug overdose. Now you see that when you use different coding, which of course you can, completely somehow distort the definition which we observed in the previous case. Also give us a new definition, so to say, among these three categories. Now the above sequence would imply a totally different relationship among the 3 conditions, right? This time the condition is completely different to what we observed last time. So if the response variable value did take a natural ordering such as mild, moderate, or severe, then 1, 2, 3 coding would be reasonable, because of course we know mild is lesser than moderate and moderate is lesser than severe, right? But right now we didn't have a natural ordering sequence. So if we don't have a natural ordering sequence, it's really dangerous if we use coding and then run a linear regression. We move on. However, for binary qualitative responses, for example, the situation is different when you are working with binary responses. And then you can think of using linear regression, right? Like 2 possibilities, for instance, with medical conditions, stroke and drug overdose, and you use some kind of dummy variable approach we call in linear regression, and you use dummy for 0 when it is a stroke and for 1 when it is a drug overdose, right? Now we can fit a linear regression to this binary response and predict drug overdose if y hat means the estimated y, is greater than 0.5. Why? Because drug overdose was equal to 1. So if I have a more than 50% chance for y, then I will go for drug overdose. Otherwise, I will choose stroke because stroke was somehow categorized as 0, somehow coded as 0, right? And notice that the x beta, which is the component in a linear regression, is in fact an estimate of probability drug overdose given x, right? However, if we use linear regression, there is a possibility that some of the estimates might go outside 0-1 interval. You may come up with some negative values, for instance, and they will be difficult for you to interpret as probabilities, right? The conclusion is that linear regression method is not a good candidate for qualitative responses, even though if we have a natural ordering, we can use that. But again, it's not a good candidate, even though. So what should we do? Well, the possible approach is to consider for some other say classification methods, some classification methods or regression based on classification methods, for instance. Like here, for each choice of predictors, now you have lots of predictors x1 to xp, we can define probability that, okay, probability that y equals to 1 given x is equal to probability of all the predictors. That a condition containing these values of predictors will yield drug overdose, because drug overdose was nominated as 1. And if y equals to 0 given x, it means I am talking about predictors which yield to the values of strokes, for instance, right? Now you have two categories, 0 and 1, and you define the probability with respect to 0 for strokes and with respect to 1 for drug overdose. So now if I say, I mean, a more mathematical term is, I said this function p has a space, the total space, which is denoted as chi over here with 0 and 1, and the desired level of certainty is again 1 minus alpha, which is exactly equal to the level of significance we taught earlier. So the classification rule is that if this function or this sample space is somehow we need to specify. So say chi1, this belong to the first category, so to say, will be the total space, based on all the predictors, and this will be the probability of all the predictors when this probability is bigger than equal to 1 minus alpha, right? So if it is bigger than equal to 1 minus alpha, I would say chi1. If it is less than 1 minus alpha, then I would say chi2, which is my another category. I had two categories, drug overdose and a stroke. So first I will achieve with this classification, and the second is the otherwise part. And now the main objective is to find this guy, this quantity. We don't know what this guy will be. So the main objective is to find out, or somehow, the estimated value of this whole function. And simplest way of doing this is taking all the predicted values in the training sample and compute frequencies, right? So now you will predict all the values and then count how many times it yields drug overdose divided by the total number of training predictors in the training sample. Similarly, number of times the predictor yields strokes, and then divided by the total number of predictors occurred in a training sample. So that's how we can define or somehow calculate the probabilities associated with each of those two outcomes, or each of those two categories, so to say. So the training sample may not have all possible values. This is again a problem, because now you are dealing with samples, so you may not have a good sample. For instance, a sample may not be a good representative of your population. So what happens that it may not have all the possible values in the predictor. And even if it has all the values that are present in the sample, it may be that too few values are involved to get an accurate estimate, right? And for these reasons, the estimate may be run unsmooth, and we cannot trust anymore our estimates, because of in general, because of the sampling error, so to say, you can say. Therefore, a better approach is needed. This approach is sufficient. One can go with this approach, but the problem is with sampling. So what should we do? We can go for a better approach, a more somehow secured approach, so to say. And that approach is logistic regression. So logistic regression is a model of choice, right? When we choose which category we should pick for a particular data. And this is very popular in quantifying qualitative responses, right? Somehow. In our example, we have binary responses like strokes when y equals to 0 and overdose when y equals to 1. So now, and all the predictors you have like that, x is all your data points. These are your patients. You wanted to know whether a patient belonged to drug overdose category or a stroke category, right? So a simple but a non-linear logit function we need to call in. So this is simple, of course, but it's not linear. So now we take a ratio of p being y being equal to 1 given all the predictors, and y being equal to 0 given all the predictors, and take a log of that, right? So this we call in mathematics as a logit function. It has a log. That's why we call it a logit function. And this function is exactly equal to some alpha, the constant values, and some function values depending on predictor number 1 up to predictor number 2. Recall what we did in our linear regression. We said y is equal to alpha plus some function of x, right? First of all, there we used a linear function, and second, the choice of f, the structure of f was not known to us, so we wanted to know a better structure of f, a better function which can somehow relate x with y, and that's what we needed here as well. So first of all, we used a nonlinear function here, and now we defined this nonlinear function with the addition of all the functions depending on individual predictors, right? Again, here we need to know what alpha is, and we need to know what would be the values of f, or what will be the function of f. So the model in general will be like that. So you have your, since we have only two categories, so say y equals to 1 and y equals to 0, two response variables. So the logit function is equal to beta naught plus functions f1 x1 up to xp fp xp, and this is called additive because each predictor enters the model individually through adding the functions, right? So now we are adding up all the functions together. So this is a nonlinear and additive function. And by the way, we haven't used any interaction terms between two predictors. So they are somehow entering into the equation individually. All the predictors are entering into the equation individually. We do not have any interaction terms between them, right? And this model will be called logistic regression if each of the functions is a linear function of x, right? Now this is being a bit tricky. So here we define a nonlinear component, but we want this to be linear. So the function of x has to be linear, for instance, you can say. And that linear function is like simply beta x1. So each beta depending on each predictor actually. So somehow each beta defines the performance, or so to say the weight of each predictors. So if I plug in all those values here, so this equation will be boiled down to this equation. By the way, I just use exponent to remove log from here, so that's why exponent comes here. This e guy comes here, and the third is if y equal, can I write y equals to 0 equal to 1 minus y being equal to 1, right? So this is that's the logic I used to simplify this equation. Now my p of y being equal to 1 given x is equal to this. So if you just simplify this equation, you will come up with this final relation. And this quantity p of x minus over 1 minus p of x, which is over here actually, is called the odds, right? And it can take any value between 0 and 1. So sometimes when you listen about betting or in some games, you listen this word, what are the odds of that particular person doing a goal, for instance, or what are the odds that that particular person will be shown as a red card, for instance. So it is this odd they are actually talking about. So if you know the data, if you have the data, you can immediately calculate the odds. And in those betting websites where you see odds defined in terms of numbers, they actually use this logistic regression to classify odds for a particular person or for a particular individual, so to say. Now let's study the topic in a more applied manner. Let's have a case study and see how logistic regression can be used in this case study, and what else can we conclude or can we extract from this data using logistic regression. So consider the default data. By default, I mean bank default, right? Where we are interested in predicting whether an individual will default on his or her credit card payment, right? On the basis of annual income and monthly credit card balance. So there are two outcomes: whether a person is going to be default or whether a person is going to be not default. So the response is default or not not default, sorry. Default and not default are my responses, and my X or predictors are income or monthly credit card balance. So I have two variables for X, which is balance and income, and there are two categories defined for my Y, which is default or not default. So if you see here, so I have made plotted a scatter diagram for balance and income, how balance and income are moving together, so to say. And I see that somehow there is a category, when you have a lots of course, when you have a lots of income, so to say, then balance is not, or you can say that somehow if you have a lots of balance over here, then you have low income. If your income is increasing, then somehow your balance or is not increasing with that pace. But when your income is really low, then you have such a high balance, like here, right? Here is a good candidate as well. But if your income was not, or if your income is too high, like here 60,000, then your balance is around 1,600 or $1,800, if I say. So that's what we do we notice in real life. If you have a high income, then you don't go for high credits. But if you have a low income, then you go for then you go for higher credits, so to say. So here is again another diagram with respect to the y, but here we only plot with one variable, 1x balance, and now you have default for like being y, being default and not default, for instance. Again, if you have a low balance on your credit card, then you are not going to default, right? And but if you have a high balance like here, then it is most likely that you will be default, right? Similarly, with respect to income, if you have a high income, then of course you're not going to default because you have the ability to pay back the amounts. But if you have well, this is a bit strange, but because even if you have a high income, somehow it says that yes, there is some chance that you are going to default as well. So just look into this diagram and try to understand more what else you can exclude, what else you can explore from this graph. Now, for a considered case, we have the response with two categories, yes and no default, for instance. Remember that rather than modeling this response directly, logistic regression models the probability that y belongs to a particular category, right? In other words, for our default data, the probability of default will be written like that. So like default is equal to yes depending on your balance, or default is yes depending on your income, right? And this probability will range between 0 and 1. Similarly, one can say default is equal to no depending on your balance, or default is equal to no depending on your income. So if somehow in logistic regression we work with probabilities, we say what are the chances that this guy will be defaulted based on his that much income, for instance, or that much balance on her credit card, on his credit card, for instance. Here we have two plots showing the default probabilities, for instance. The left hand plot shows the linear regression fit here. So what we did actually, we fit a linear regression to the default data, and we use this like so to say this coding to run a linear regression, and we clearly see some of the probability values are beyond the expected range. You see here, like here on that region, we have some negative probabilities, for instance, which is not possible. And this happens because we are somehow forcing our data to follow a linear regression pattern, which is actually not. It is not linear, it is non-linear. Somehow we are forcing data to follow linear regression, and that's why we see that some of the probabilities are negative. The right-hand plot shows a logistic regression instead to the default data. And the logistic function will always, remember that this will always produce an S-shaped curve, like here. See the S-shaped curve is coming up here. And if you see always when you run logistic regression, you will see this similar type of curve. Notice that for low balance, the model predicts the probability of default as close to, but never below 0, of course. So again, when you have a low balance, the probability of default is almost 0. Again, not negative, but almost 0. But if your balance is increasing, the probability of default is also increasing, right? And here you attain a maximum balance on your credit card and see that your probability of default is almost 100%. Likewise, for high balance, it predicts a default probability close to, but never, of course, above 1, right? So the logistic regression or logistic model is better um, able to capture the range of probabilities within the within the range defined than the linear regression model. Now let's analyze the values. So now once I run the logistic regression, I got those values for my intercept, which was my alpha. And by the way, I only used one predictor right now. I only use balance as a predictor. So these are the coefficient values for my intercept and balance. P-value is of course much less than 0.05. It means both of those variables are significant, right? And once we construct our estimation table like this, it is simple to compute the probability of default for any given credit card balance. And this is a beauty. Now you have a model, so you plug in any credit card balance, and from this table you can evaluate what are the chances of a person being default based on that particular balance, for instance. For example, using the above coefficient estimates, we predict the default probability of an individual with a balance of $1,000. You had a data, and based on your data you build a logistic regression model. You estimate your parameters, and now you wanted to calculate for any random value of balance what will be the probability of default, right? So now remember the model. Now we have only one predictor, which is x1, and that predictor is balance. Beta naught is this guy, minus 10.65, and beta 1 is 0.0051. So this was your model from our previous slide for one predictor. So we plug in all the values here. So E is as it is, beta naught is this guy, beta 1 is 0.05, and x1 0.005, and x1 is 1000. I wanted to know what will be the probability of default based on this balance. Right? I plug in values over here as well, and I see that the probability of default with this batch balance is really low, much less than 1%. Right? Now, go back to our previous graph and see what was the probability of default when the balance was $1,000. So almost zero, right? And that's what we see here. It's very close to zero, much less than 1%. In contrast, the predicted probability of default for an individual with balance of 2000 is much higher. So now just plug in 2000 over here, and then you will get this value, 58%, almost 59%. And if you look back in the previous graph, you see that when it was 20,000, the balance, the probability of default was somewhere here, almost 60% or 59%, right? And that's what we can see from those values. So now, being a good model, logistic regression model for any balance, any value, one can immediately check what are the probability of defaults. We move on, and then we specify more. We say that, okay, what if we have qualitative predictors in the data? For example, a dummy variable approach can be used for such predictors. And in our case, the default data set contains the qualitative variable student, for instance, right? Now, to fit the logistic regression model, we simply create a dummy variable that takes on a value 1 for students and 0 for non-students. So now we further somehow specified our default being qualitative, for instance. So if now I plug in all the values in my model, and then I calculate my intercept beta naught and student. When it is yes means when it was a student, when the guy was a student. P values are much lower. Both are significant, of course, and you know that when somebody is a student, chances are more likely that he or she will get default, because you need to somehow cover your expenses, but you don't have income, for instance, or maybe you may not have a high income, for instance, right? So now the coefficient associated with the dummy variable is positive, of course. This guy is positive, and the p-value is of course significant. Now, probability of default when default is yes, and then student, well, the guy was a student, right? And again, probability of default when default is yes, but the guy is not student, and we can just plug in values over here. So I use the same model, but here I'm using 1 and 0 for those dummies. So when a guy was a student, I used dummy equals to 1, and when a guy student was not student, I used dummy equal to 0. And here are the probabilities. This indicates that students tend to have a slightly higher default probability than non-students, right? So that's how we can somehow dig into the problem and then evaluate or classify probabilities. Multiple logistic regression, when you have lots of predictors. Again, as we discussed, multiple linear regression. But now our, of course, model is not linear anymore. So now we consider a problem of predicting a binary response. Well, by the way, we are talking about binary response, only two possibilities, default or not default, using multiple predictors. So again, the formulation is exactly the same, but now you have lots of betas and lots of x. Final relation is exactly the same, but we have lots of more beta and of course x. So now in our case study, we now have three predictors, say balance, income, and student, right? And the task is to find the probability of default. So I plug in all my variables into a model, and then these are the values. So intercept is this beta naught, balance is beta 1, income is beta 2, and student, yes, when I use 1 for student, is beta 3. So here are the responses, the estimates of coefficients, and p-values are here. So I can see that balance is of course highly significant, income is not very significant, and students, when a person was a student, is also highly significant. Now let's evaluate the probabilities. So the p-value associated with balance and dummy variable student, of course, are very small, indicating that each of these variables is associated with the probability of default. Those variables are somehow linked with default. If a person is a student of a person has a low balance, then it's more likely that he or she will get or will be default or will be a defaulter after some time. However, the coefficient for dummy variable is negative. Notice here, right? Indicating, so this guy is negative, indicating that students are less likely to default than non-students. In the previous page, I don't know exactly the page, I think this was not page number 25, but we can go back and see. Yeah, here, page 15, sorry. On page 15, it was positive and it was 40%. So what happened here? So in the previous table with students, and the parameter was positive, but now it is negative. So how is it possible for student status to be associated with an increase in probability of default in previous table and a decrease in probability of default in the extended table, like here? So what do you think? What could be the possible reason of this change in the sign of parameter, so to say? Well, let's dig into it and try to understand the consequence. From a left-hand plot, we see that student default rate is at or below that of non-student default rate for every value of balance. So now you have default rate and now you have credit card balance, but here we have two graphs. One is for not student and one is for student, for being student. And we see that the student default rate is up here. The blue line, of course, the orange line is a student line and the blue line is for the not student line. However, the horizontal broken line, those lines near the base of the plot, shows that default rate for student and non-student averaged over all the values of balance and income suggests the opposite effect. Here the brown lines are higher and green lines are lower, but here the brown lines are of course lower and the blue lines are higher, right? So consequently, there is a positive coefficient for a student in the single variable logistic regression output shown in previous page, like page number 15. And even if you look here again, you will see the same status coming up here. Like for no students, credit card balance is a bit higher, and for students, of course, it is also almost the same. So as I said, the overall student default rate is higher than non-default rate. So when you plug in like income and balance all together, you see that it changes slightly because of course income is one variable which we haven't included, and also balance is one variable which we haven't included in our previous table, and that's why the effect was positive. But when we included them in our model, we see a negative effect, somehow a different effect. and I would say that effect is the overall effect because of these dependents, so to say. Now consider the right-hand plot. It provides an explanation of this discrepancy. Students who are more likely to have large credit card balances, like here, tend to associate with higher default probabilities or default rates. Thus, even though an individual student with given credit card balance will tend to have lower probability of default than non-students, the fact that students on a whole tend to have high credit card balances means that overall students tend to default at a higher rate than non-students. And again, because of the dependence between income and balance with the students. So student is riskier than non-student if no information about credit card balance is available. However, that student is less risky than non-students with the same credit card balance. Of course, when you have a same credit card balance, you chances are less when you are a student to get default. But if there is no information available, chances are that a person being a student gets a higher have a higher probability of being default, so to say. So just go through this example very carefully, read between the lines, try to understand those graphs and see what happened. And also from the table, how you can use those values in the table to evaluate probabilities. Try to understand the model. Now, by substituting estimates from the regression for the regression coefficients from table on page 26 and 27. By the way, I see that I keep having wrong page numbers. I will correct them in the PDF file when I upload the PDF file. I didn't notice when I was started recording the video lectures, but I will do that. So when you are listening to my video lecture, do refer to the PDF related to this topic. Do not look on those on these slides because I see that page numbers are not correctly defined. For example, a student with a credit card balance of that much and income of this much has a estimated probability of default. So now what we are doing, actually we are plugging in all the values. So this was our model. If you go back, this was our model, beta naught, beta 1, beta 2, beta 3, right? And we have some values for like balance and income. And for student, well, I say student, it means I will plug in 1 for students. So this is beta naught, beta 1 times this guy, beta 2 times 40 if I say in thousands, for instance, and then beta 3, which was negative, times 1 for my student, for being student. And for non-student, again I plug in 0 over here. So these are the probabilities. I multiply the income coefficient estimated by 40 rather than 40,000 because the income data was actually measured in $1,000. So instead of 40,000, I said 40 here, right? Because it was measured in 1,000s. So far, we have been discussing the cases when the response has two categories, right? Like default or not default. But in real world, we sometimes classify responses in more than two classes, right? For instance, in our previous example with medical conditions, strokes, drug overdose, and epileptic seizure was involved. So if we wish to model, for instance, according to logistic regression idea, what will happen? We will see probability of Y being stroke depending on X and Y being overdose depending on X, while the remaining will be probability of Y being epileptic seizure depending on X, which is equal to 1 minus this probability minus this probability, because the total is of course 1. And such a classification is referred to as the multiple class classification when we have more than two classes. And the method named as discriminant analysis is popularly known for such classifications. We are not going to discuss this in detail in this course, but just to give you an idea that when you have more than two classes, you have to somehow resort to discriminant analysis. In real world, sometimes we need with data that is qualitative in nature, such as gender, ethnicity, regional divisions, for instance, etc., etc. So now, like here, balance, age, cars, you have lots of variables, right? Some are qualitative, some are quantitative. So for such variables, one needs to create a dummy variable and then fit a regular regression model. right? By the way, we are talking about predictors, not talking about responses. So when your predictors are qualitative, just use dummy variables like 0 and 1, and then somehow, as we did with students, like 0 for a student and 1 for not student. Right? So in your predictors, you can use dummy variables or you can use coding to somehow define qualitative variables into quantitative and then use a simple linear regression. However, the interpretation of coefficients associated with such variables depends heavily on how your dummy was created. If you say 1 is for student, then you are talking about students, for instance. So you need to remember what type of codes you used for defining the dummy variables. So like here, these two slides are for regression with qualitative predictors, like for genders, for instance. So if a person is male, I said 1. If a person is female, I said 0, right? And then this will be my regression. So if a person is female, this is the regression model. And if a person is male, this is my regression model. So I just plug in those values 1 and 0 into my X and then evaluate the prediction, evaluate my models. Now, see, alpha can be interpreted as average credit card balance among sales, and alpha plus beta as the average credit card balance among females, right? And beta 1 is the average difference in the credit card balance between males and females, and that's what you can see over here, right? So if I have some kind of table like that here, so the average credit card debt for male is estimated to be 590. By the way, I'm talking about male, even though this represents intercept. This represents intercept because if you see here, alpha was associated with my model, but with males. Like for when I use 0 for in 0 in my predictors. So this alpha is actually defining everything about male, and this alpha plus beta 1 is defining me everything about female, right? Again, so and whereas for females are estimated to carry this 19.73, so the total debt is the sum of those two quantities, and p-value for dummy variable is very high, indicating that there is no significant difference in average credit card balance between genders. So things like that we can somehow do when we have qualitative predictors. So just go through this lecture on logistic regression. I don't think it's too difficult to grasp, but read my notes and also listen to the lecture. Try to understand figures and tables, the model, the way model was written, because this information will be required for lab number 4, and also you may need this in your final project. Thank you very much.